Hello, my name is John Cutrone, and this is Lab 3, Magnetic Field of a Bar Magnet. The main goals of this lab are to observe the distance-dependence relationship of a magnetic field from a bar magnet, create a simulated model of a bar magnet with VPython and GlowScript, and collate the observed and simulated magnetic field magnitudes. Some findings are, as the distance decreases, the magnitude of the magnetic field increases, and the magnitude of the magnetic dipole moment is 3.571 amperes per meter squared. The experimental off-axis magnetic field magnitude is 3.83 times 10 to the negative fifth teslas, and the simulated off-axis magnetic field magnitude is 6.22 times 10 to the negative fifth tesla. Some main concepts that are explored in this lab are the Biot-Savart law, a law that calculates the magnetic field of a current carrying segment from a certain distance away from the observation location, and the magnetic field dipole equations, which are shown below, where the magnetic dipole on axis is double the magnitude of perpendicular. In addition, the magnetic dipole equation is shown, where the direction of the on-axis magnetic field is the same as the magnetic dipole moment and opposite for a perpendicular axis. In addition, a magnetic field equation for a bar magnet or dipole is shown with kr to the n, which is equivalent to ln of bx equals ln of k plus n times ln of r. In addition, the general equation for the magnetic field from a magnetic dipole is shown below. The procedure of this experiment is, after downloading the magnetometer app, the location of the actual magnetometer was found by calibrating the phone horizontally and vertically until the position of the strongest magnetic reading was found. Next, the magnetometer was moved at different distances across the meter stick on axis in accordance with different magnetic field readings from 20 to 220 Tesla. Finally, the off-axis magnetic field was found by finding a perpendicular distance when the magnetic field equals 100 Tesla, taking another meter stick and moving the magnetometer upwards to create a 45-degree angle with the same distance up and record the measurement. The primary assumption is that the bar magnet that was used in the experiment was an ideal representation of a magnetic dipole. Here's a simplified model of the systems and surroundings. The system is the observation point being affected by the magnetic field, which is the magnetometer, and the surroundings is the bar magnet, which affects the system with this magnetic field. The red arrows represent the magnetic field lines, and the pink one represents the dipole moment direction. Some observations from the experiment: as the magnetometer moves away from the magnet, the x component of the magnetic field approaches a near zero magnetic field magnitude, and as the magnetometer moves closer to the magnet, the x component of the magnetic field increases in magnitude. Overall, there's an inversely proportional relationship between distance and magnitude. Here's my magnetic dipole experimental data with all of the data shown and a graph representing the data with the equation, which that equation is used here. The distance dependence equation was negative 2.67x minus 14.2. ln of k was equal to the y-intercept, and the slope was equal to the negative 2.67. And you set the kr of n equal to the B dipole on axis equation to find the magnetic dipole, which is equal to 3.571 amperes per meter squared, and the magnitude of the off-axis magnetic field using the data that I showed before. The magnitude was found to be 6.22 times 10 to the negative fifth. Here's some of my GlowScript showing the constant, including the magnetic field constant, and the dipole function that I used, which is equivalent to the one I showed. And I made observation locations on axis and perpendicular and made different arrows correlating. And I did the same thing with off-axis magnetic and made this model. The results of the experiments, as I said before, an inversely proportional relationship between distance and magnetic field magnitude. The magnetic dipole moment was 3.571. The experimental data is shown and the computational magnitude is shown with about 38.4%. Possible sources of error: the magnetometer might not have been completely accurate, the table might not have been level, the electronic devices may have interfered. If we hadn't oriented the experiment to compensate for north, the data would have been skewed, and if two magnets were put together, then the magnitude would have doubled.